Geometry, Chapter 10, Lesson 3, continuing to look at area. And in this lesson and the next one, we want to look at a formula that allows us to calculate the area of a regular polygon. Now, we've looked at squares, which actually are regular polygons. We've looked at parallelograms, which can be regular polygons if they're a rhombus or a square. Triangles, which can be regular polygons. Trapezoids, which cannot be regular polygons but are polygons. And we have formulas for those. The formula that we're going to look at in these next two lessons can be used for any regular polygon. So they can be used for squares and rhombi, and they can be used for triangles that are regular, but most often we're going to use these for polygons with more than 4 sides, pentagons, hexagons, octagons, those types of figures. But we will use them for regular triangles as well. So even though we have a formula that's specific to triangles, this regular polygon formula can apply to any polygon that is regular, and we'll talk about what that is in a few moments. Before we look at the formula specifically, there's some vocabulary, new vocabulary that we're going to need to look at, but we also want to review some vocabulary that we've had in the past so we're clear on what we're talking about. So let's do that first. When we're talking about a polygon, we're talking about a figure that's a closed figures. The sides are segments. There has to be at least 3 sides. The sides can only intersect at the endpoints of those segments, and none of these sides can be collinear. So you can't have a side on top of a side. Now, what makes the polygon regular? Because our formula that we're going to use can only be used for regular polygons. And regular polygons have 2 characteristics. The angles inside the polygon are all the same measure, and all of the sides are the same lengths. So any polygon that meets those 2 criteria is regular. Now, in order to use the formula that we're going to be talking about, this is very important that we make sure it's regular, because one part of the formula requires us to use the fact that the sides are congruent in order to determine the number that we need to substitute in. So it's important to remember that this formula we're going to be talking about is only for regular polygons. Now, let's take a look at some of the new information, and we're going to kind of build step by step here. So make sure you get each step as we go forward. The first thing we want to look at is the fact that if we have a regular polygon, 6 sides, 7 sides, 8 sides, 9 sides, 10 sides, doesn't matter. If it's you can circumscribe a circle. You remember from earlier, circumscribe means to draw around, and you can draw a circle so that the circle touches each of the vertices. Okay? And again, you can do this with any polygon, regular polygon. The fact that you can draw a circle around this, the center of the circle becomes the center of the polygon as well. So drawing this circle around so that it touches each of the vertices gives us the center of the polygon. Now, if we think about a radius, if we draw a radius that goes from the center of the circle to the circle. If we draw a radius from the center of the polygon now to the vertex, that radius of the polygon is also the radius of the circle. So if we know the length of the radius of the circle, we also know then the length of the segment that goes from the center of the polygon to the vertex of the regular polygon. So the radius of the circle matches the distance from the center of the circle to a vertex. And again, this is very important. And circumscribing the circle helps us to do that. Now, why would we want to do that? Well, if we draw a radius to any vertex, all right, what do we create? We create these triangles inside the regular polygon. Don't worry about this word up on the left here. We're going to talk about that in a moment. But if you draw all the radiuses, or a radius from the center to each vertex of the polygon, you'll notice that you create these triangles. And all of these triangles are equilateral, or I'm sorry, isosceles, because these 2 sides are the same length because they're both radii of the circle. And the radii are the same length in a circle. So you create these isosceles triangles, which again has some properties that again are going to allow us to do and to calculate some values that we're going to need for our formula when we get to it. Now each of these triangles has the exact same area. They're all congruent triangles. So if I were able to calculate the area of one triangle, multiply it by how many triangles there are, that would be one way to find the area of the regular polygon. That's not the way we're going to do it, but that would be a way. Now, let's look at this other word. If you draw a segment that goes from the center of the circle, which is also the center of the polygon, perpendicular to the side, okay, this is what we call an apothem. Okay, so this is a new vocabulary word, an apothem. The apothem goes from the center of the circle perpendicular to the side of the regular polygon. Now notice that is different than a radius. A radius goes to the vertex, an apothem goes perpendicular to a side. Radius to the vertex, apothem perpendicular to the side. Radius perpendicular, no, radius is to the vertex, and apothem is perpendicular to the side. Okay, so we just want to keep those two different lengths in mind. Our formula is going to be concerned with one of these specifically, not the other. However, one is going to help us determine the other in a lot of cases. So we need to know the difference, and we need to know that when we're looking at a diagram, if I'm looking for the apothem, I need to find the right angle symbol in the diagram. Once I find the right angle symbol, then I can find the apothem. The radius is not perpendicular, so there will be no right angle sign in relation to the radius. Okay? So radius goes from center to vertex, apothem goes from center perpendicular to the side. Now notice what you create when you draw this apothem and the radius together. You create this right triangle. And again, right triangles are very valuable to us because it then allows us to use things that we know from our past. Three types of things that we can use: the Pythagorean theorem, which will allow us to determine the lengths of any sides of this little triangle. We may be able to use 30, 60, 90, or 45, 45, 90 if one of these angles happens to be one of those. Or we can use trigonometry, sine, cosine, or tangent, because we have a right triangle. So creating right triangles is very important. So it takes an apothem and a radius to form a right triangle. I want you to notice one thing about what we talked about earlier, this radius that goes to any vertex. Notice that these are not right triangles. Even though they're isosceles and congruent, they're not right triangles. So we cannot use Pythagorean theorem when we draw two radii. We cannot use trigonometry when we draw two radii, and we cannot use 30, 60, 90, or 45, 45, 90s when we draw two radii because a right triangle is not created. However, if I draw an apothem with those, I do create these little right triangles wherein I can use those. Okay? So it's very important to understand the difference between a radius and an apothem and to realize what each one does.